Hello learners, in this video we are going to see correlative coding. Correlative coding, the other name of correlative coding is called as partial response signaling. Here in correlative coding is nothing but adding the ISI to the transmitted signal in a controlled manner. That means adding the intersymbol interference to the transmitted signal in a controlled manner is called as correlative coding. And by using the correlative coding, it is possible to achieve bitrate to B naught bits per second in a channel and bandwidth equal to B naught seconds. Here, this intersymbol interference is introduced in the transmitter side. It can be compensated at the receiver side. The correlative coding is the theoretical value is possible. That means the maximum signaling rate to P naught bits per second and bandwidth P naught hits is possible by using the reliable perturbation tolerance filter. First, correlative coding is binary signaling. In this duo, it mentioned doubling of transmission capacity of the straight binary system. The basic idea of correlative coding is explained the duo binary coding. In this duo binary coding, doubling of transmission capacity of the straight binary system. In input binary sequence PK is consist of uncorrelated binary digit with the duration of TB, and simple 1 is represented as +1, simple 0 is represented as -1. The sequence is applied to the duo binary encoder. It is converted into 3-level output -2, 0, +2. We'll see. Consider the sequence 00. Consider the sequence 00101110. Here the binary sequence is 00101110. For here we can convert the polar amplitude. If it is 0, -1. If it is 1, +1. So the 0 is converted into -1, -1, +1, -1, +1, +1, -1. In correlative coding, here it will add the correlation between the input sample. How it add the correlation between the input sample means Vk is added with the previous value. That means this is the previous value. Previous value is added with the next value. Okay, -1 it is -2. -1 +1 it is 0. -1 +1 -1 it is 0. -1 +1 it is 0. +1 +1 it is 2. 1 minus 1 it is 0. It is the encoder transmitter signal. At the receiver side, the decision rule, decoding decision rule is Ck equal to 2 if Pk is equal to 1. Ck is equal to 2, then Pk value is equal to 1. Ck value is equal to -2, it decides that Pk value is equal to -1. If Ck value is 0, then it decides the opposite value of the previous decision. Now the received signal is -2, 0, 0, 0, 2, 0. This signal is received. And then how the decision is happen means if -2 means it is -1, if it is 0 means opposite of the previous value, if -1 means it is +1, here +1 means -1, -1 means +1. And then if 2 means it is binary value 1. If 0 means it is opposite of the previous value. Here it is 1, therefore it is -1. And then we decode the binary sequence. If -1 means 0, +1 means 1. Here 0, here 1, here it is 0, here it will be 1, and here it will be 1, here it will be 0. This is the duo binary coding. In this duo binary signaling, here duo is implies that doubling of the transmission capacity of straight binary system. Here, this is the duo binary signaling. In this duo binary signaling, the input signal level AK is given into the summer, and then the delayed 1 dB. 1 unit delay function is also, that means the previous value is given into the summer, and then it will add two value, and then the output is given into the ideal channel. This ideal channel is high Nyquist channel and then H Nyquist channel. Then the sampling output is taken for every kTb time second and the output sequence is transmitted through the channel. Okay. Here the binary sequence is considered as here the binary sequence PK. It is the uncorrelated binary signal 0 1. If it is PK, if the binary sequence is 1, then AK value is plus 1. If binary sequence is equal to 0, the AK value is minus 1. And then CK is equal to AK plus AK minus 1. This AK is the present value, AK minus 1 is the previous value. This previous value is added with the present value to get the CK value. The binary signal PK is first applied to the simple filter with a single delay element. The unit impulse is applied to the filter to get two impulses. That means present value and then past value. Here the CK is the output of the duo binary coder. It is the sum of present binary digit plus previous binary digit. So CK equal to PK plus PK minus 1. The correlation between the adjacent transmitter signal is introduced in ISI. This intersymbol interference is introduced in the transmitter side by artificial manner, and then this ISI is under the design control, which is called as the basic of correlative coding. That means the intersymbol interference in the transmitter channel is added in a controlled manner. It is called as correlative coding. The ideal Nyquist channel bandwidth W equal to 1 divided by 2p. H of I is equal to the ideal Nyquist channel H of I equal to H of Nyquist into 1 plus exponential of j 2 pi f tb. Here Here, one of the signal is 1 and another signal is produced 1 delay. That's why only it is called as 1 plus e power minus j 2 pi ftb. So the high hi Nyquist is equal to h Nyquist is equal to hi of f equal to Nyquist h Nyquist of f exponential of here we take e power minus j term outside e power. Here we take e power minus j term outside. So here this one will be e power plus j pi fb plus e power minus j pi ftb exponential of minus j pi ftb. Here this we know that the exponential e power minus j theta plus e power plus j theta is equal to 2 cos theta. So we apply this formula, we get 2h Nyquist of f is equal to h of cos of pi ftb into exponential of minus j pi ftb. And then this is the Nyquist function. The Nyquist function is h Nyquist is equal to 1 for modulus of f is less than or equal to 1 divided by 2 dB, 0 otherwise. We substitute h Nyquist, hi of f is equal to 2 cos of pi ftb exponential of minus j pi ftb. It is for the interval modulus of f less than or equal to 1 2 pi tb and it is 0 otherwise. And hi of t, this is the time domain function. In this time domain function we consider the rectangular function, and the rectangular function, it is the time domain function. We consider the two function. One is present value and previous value. Present rectangular function. If we take the Fourier transform of rectangular function, we will get the sinc function, and this is the sinc function. H of it is equal to sine of pi t divided by tb, pi t divided by tb plus one previous function sine of pi into t minus tb divided by tb, the whole divided by pi into t minus tb divided by tb. This is the previous sample value and this is the present sample value. If we take the LCM, we will get t square sine pi tb, t square sine pi pi t sine pi t divided by tb, the whole divided by pi t into tb minus t. This is the This is the time domain function. This is the impulse response of duo binary conversion filter. This is the impulse response of duo binary conversion filter, and this is the frequency response of duo binary conversion filter. This is the amplitude response, and this is the phase response. In a tail of hi of t is the decay of 1 divided by t square. So it will produce a faster rate of decay than the ideal Nyquist channel. And here AK cap is represent the estimated of the original pulse, and it is considered in the receiver side, and AK equal to CK minus AK minus 1. Here, decision feedback. Decision feedback, it is the technique used to estimate the previous symbol and propagate. If one error is possible, that error is propagated through the output. Pre-coding. Pre-coding is nothing but it is the practical means of avoiding the error propagation phenomenon before the duo binary coding. Now we will see pre-coding. This is the precoder. This is the precoder. In this precoder, here the PK signal is given into the XOR gate, and the output of the adder is the previous value of DK is given into the XOR gate, and then same structure is used in the duo binary coder. This is the duo binary coder, and this is the precoder. Precoder is mainly used to eliminate the error propagation at the output side. Here dk is equal to pk XR function of t into k minus 1. Here tk is equal to symbol 1 if pk and dk is 1. If it is 0, otherwise. If any of the function pk or tk minus 1 is 1, at the time the symbol 1 at the time, the simple 1 is propagated. Otherwise, simple 0 is propagated. Here, TK is applied into the pulse amplitude modulator and producing the two-level shot plus AK is plus 1 and minus 1, and CK is equal to AK plus AK minus 1, and CK equal to 0 if the PK value is 1, plus or minus 2 if the data symbol PK is 0. This is the decoder for recovering of original binary sequence from the pre-coded DO signal. Here we already see that CK is given into the rectifier, and then CK value is AK plus DK, and if CK value is less than 1, then the and if ck value here if the ck value is less than 1, then then it is the binary 1. If ck value modulus of ck value is less than 1, then it is the binary 1. Modulus of ck value is greater than 1, then it is the binary is 0. Here it is given ck value is 0 when pk value is 1, ck value is plus or minus 2 when pk value is 0. If we take the magnitude, say magnitude of ck is less than 1, then the pk value is transferred. If the magnitude of ck is greater than 1, then pk is equal to 0. Now we see modified duo binary coding. In this modified duo binary coding, it gives the correlation of two the correlation span of two binary digits. Okay, here it subtract the here here if this modified duo binary signaling is achieved by subtracting the input binary digit 2 dB spaced apart. The output of the duo binary conversion filter is linked to the AK. Here, in last binary sequence, CK equal to AK plus AK minus 2. Here, CK equal to AK minus AK minus 2. Here, three-level signal is generated. For AK is equal to plus or minus 1 volt. CK is take any one of the three value. 2, 0, minus 2 volt. This is the modified duo binary code. In this, this is the precoder. In this normal duo binary code, the delay is 1 dB. Here in modified duo-binary signaling code, the delay is 2 dB. Here this is the precoder. This precoder is used to reduce the error function. And then here the PK is, this PK is XOR function with the TK minus 2. That means here the output of the XOR gate is TK. The previous value, the 2 dB previous value is taken and it is given into the XOR code. So PK is equal to PK XOR with PK minus 2, and then pulse amplitude modulation is provide the sequence in AK, and then the AK, here the CK value, this is the output function, and output function CK is equal to AK minus or minus of AK minus 2. uh, this is the ideal channel. Ideal channel is produce the Nyquist response, Nyquist pulse. Now the sample is taken for the output sample is taken for every KTB time period. The output of 3-level sequence is equal to CK. That means the 3 level is nothing but plus 2, 0, minus 2. And modified bio-binary signaling. In this modified bio-binary signaling, non-zero at the origin, it is undesirable. Non-zero at the origin is undesirable. Here, the subtracting the amplitude modulation is modulator pulse spaced to 2 dB second. That means CK is equal to AK plus AK minus 1. And H4 function is equal to, here this is the class 4 function. Class 4 function is equal to H of 4 F equal to H Nyquist of 1 minus exponential of, here here it will be a k minus 2. Here it will be a k minus 2, and 1 minus exponential of minus j 4 pi ftb, and then we know that here we take e power minus j to be in outside. If we take e power j to be in outside, we will get e power plus j to 2 pi ft minus e power minus j 2 pi ft, and we know that e power j theta minus e power minus j theta divided by 2, 2j is equal to sin theta. Here we can convert that form. 2j equal to h Nyquist of f into sine of 2 pi ftb exponential of minus j 2 pi ftb, and then the Nyquist function, by applying the Nyquist function, we know that Nyquist function is equal to 1 for modulus of f is less than or equal to 1 divided by 2 dB. So the h fourth of function f is equal to h of f is equal to 2j sine 2 pi ftb exponential of minus j 2 pi ftb. Modulus of f is less than or equal to 1 divided by 2 dB and 0 elsewhere. If we find the time domain function, we will get sine pi t divided by tb, the whole divided by pi tb, pi t divided by tb minus sine pi t minus 2 tb divided by tb pi into t minus 2 tb divided by tb. If we take the LCM, the function is simplified into 2 tb square sine pi t minus tb divided by pi t into 2 tb minus 1. And the precoding function, this is the function of precoder. Precoder is equal to dk equal to pk XOR gate of XOR function of pk minus 1. The symbol is equal to 1 when pk, either of the symbol pk and tk is 1 and 0 otherwise. And this is the frequency response of the modified duo-binary coding. Here the here at zero function, at zero frequency, the output is equal to 0, and this is the phase response of the duo-binary coding, modified duo-binary coding, and this is the impulse response of the modified duo-binary coding. And this is the random case. The random case CK equal to 1, CK equal to 1, the random case in the favor of symbol 1 or symbol 0. If modulus of CK is greater than 1, then the PK is equal to 1. If modulus of CK is less than 1, the symbol pk is equal to 0. And this is the generalized form of correlative level coding. In this centralized form of correlative level coding, here ck equal to 1 for random case in the favor of symbol 1 or 0. Here this is the class type. Here this is the, if the weight V naught W naught W1 is equal to 1, then it is the duobinary coding, and W naught equal to 1, W 1 equal to 0, W2 equal to -1, then it is the modified duobinary coding. It is the class. This is the type of class for a correlative level coding. Here, in this correlative level coding, here it has more number of delays added. If it is one delay means, then it is the duobinary coding. If it is the two delay function means, then it is the modified duobinary coding. And then weight is applied in every delay function. And here this is the function. The function h of t is equal to summation n equal to 0 to n minus 1 wn sinc of t minus t divided by db minus n. Thank you.